Yeah, so today we're gonna look at another duality between moments and coefficient. And just recall that we found a duality between mixed moments and coefficient, right? As matrices, they are inverses of each other. And today we will find another duality between moments and not mixed moment, but just moments and coefficients. Okay. So theorem. Actually, this theorem we proved before. So L is a linear functional. With moment sequence mu n. And we assume that the Henkel determinant is non-zero, and we know that there is a monic OPS. Then the monic OPS we know there is unique monic OPS for L is given by this formula. Pn is 1 over the Henkel determinant of size n-1 determinant of this matrix. Mu0, mu1, dot, 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 mu n. Mu1, it's just like Henkel determinant, except the last row is 1x dot 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 x to the n, like this. So if you expand this as a determinant, if you write down this determinant expression, then you get a polynomial in x of degree x to the n. The highest term has coefficient this delta n-1 doesn't cancel with this. It's a monic polynomial of degree n-1, degree n. And we actually prove this using the fact that there's a unique orthogonal polynomial sequence and these satisfy the orthogonality. Okay? But we will prove this combinatorially using the LGV lemma. And as usual, we write k from 0 to n, nu and k, x to the k. So nu and k are the coefficients of the orthogonal polynomial Pn. And so we need to prove the theorem is equivalent, restated. If we restate the theorem, we can write that as follows. So what is the coefficient of x to the k of this? So if you want to get x to the k, you have to select x to the k here in this last row expansion. Then you get the matrix, the determinant of this matrix. So that's exactly this, delta n-1, and we have the coefficient, the sign n-k, and what we are left with is exactly the Henkel matrix where we select rows from 0 to n-1, columns 0 to n except column k. So that means we can write down this as a Henkel matrix minor, where the row indices are like this, n-1, column indices are, let's write this, that means this is missing. So remove the kth column, okay? So these two are equivalent, okay? So we will prove this. And because this looks like a Henkel determinant of some indices, if you remember, we did find Henkel determinants, something similar to that. For example, the simplest case being this. We select the consecutive rows and columns from the beginning, then we get a nice non-intersecting lattice path business. And also we found, what is it? This. The rows are still from 0 to n, but we just removed n, the column n. But in this case, in our case here, is kind of a generalization of that, because we can remove any element in this column. So if you choose this to be just n, then we get the original one, and if you choose this to be n minus 1, then we get the other Henkel type determinant. So we have a more general situation now. Okay, but the idea is still the same. Let's look at this. K n. This can be written in this way. So determinant of mu I plus j, but I'm gonna write some notation just for convenience. J greater than or equal to k ij from 0 to n minus 1, where this chi means chi of a statement is here, 1 or 0, 1 if p is true, if p false. Okay, so it's a notation that we're going to use. So if j is greater than or equal to k, instead of this, we add one more. So if we don't have this is exactly the Henkel determinant. We have some kind of shifting for the column indices j. And we can model this using lattice path. So let A, this boldface A to be, so it goes from 0 to n minus 1, and B, but just to make sure that we have some index k involved, let me write B super k, B0 up to Bn minus 1, where A, I is as usual minus I comma 0, B, I is I plus this kappa, chi, j greater than or equal to k, comma 0. That means we shift this by 1 if j is greater than or equal to k. Yeah, okay, that's right, j. Yeah. So then this thing over here is exactly the generating function for all, the matrix of this, but this is exactly the generating function for all paths from AI to BJ. Okay, so what I say is that this is the generating function for all lattice path, but by LGV lemma, this is the generating function for all non-intersecting path from A to B, BK, where we have to multiply sign and the weight. Okay. But let me just draw an example. Let me give you an example just to, I think I need to draw this nicely. So A5, A4, A3, A2, A1, A0 equals B0, B1, B2, so K equals 2, so B2 is here instead of this, P3, P4, P5, like that, okay? And we want to consider non-intersecting lattice path from here to there. So this has to be a fixed point, just a single path of length 0. This must go up and down. These are fixed. And also, by the way, these are all fixed. We don't have much choice, but we have to go all the way up until this x equals 0 line. We don't have any choice but going all the way over there. Okay. Draw a little better. Okay. Now we have some choices. So let me use this example. This, this, and this, like this. Up, horizontal, and then down like this. So we have a non-intersecting lattice path like this. Although they have some crossings, it's considered to be a non-intersecting lattice path because the vertex, they don't share any common vertices. So that's what a non-intersecting lattice path means. All right. Now we need to investigate non-intersecting lattice path. We need to find some properties of this. So to do that, let me Ri, let's define Ri, some region, this is 0, I minus 1. Let's say this is the region Ri. And we want to look at what these look like. So here is, let me just write down, that's it. 1, 2, 3, 4, 5 height. So this is R1, R5. This is R4, etc. This is R1, etc. Okay. So we're gonna have a bunch of observations. Observations. 1. Oh, and these are, this is P0 up to P n minus 1, where the starting point of Pi is Ai, like this. And the first observation, the simplest observation is, if you have Pi, it starts from Ai, and the first I step must be an up step, must be all up steps. So Pi has I up steps at the beginning. At the beginning, okay? These are all fixed. And second, now we look at, most of the time we will look at this part, Ri, where R is greater than or equal to 1. So Ri, there are n minus I path having a step, having steps, at least one steps in Ri. So for example here, at least one step, let me write that more precisely, at least one step in these are basically actually P I P n minus I are those. So for example here we have only these paths have steps in this region, because if you these things cannot have a step over here, but they have to go somewhere in this region. So that's what it means. It's just simple observation. And this is an interesting thing. Let's say D equals number of downs in Ri, and U number of ups in Ri. Then D minus U is always 1. n minus y. Why is that? Also, for instance, this. We have 1, 2, 3 down steps, d minus u 0, so 3 minus 0 is 3, right? That's n minus 3. But what that means is, if you look at this, from this observation, we know that this path must have at least one path over here, one step at least. They may be more than one, because this can go down and then go up, right? But for any path, for instance this, for any path, even if it goes down and go up again, it has to go down again, because eventually it will exceed this line. So if you consider the first entering point and then exiting point, we must have plus one more down steps than up steps. For every path, its contribution to this is 1, because down is always one more than up. So that's why this is true. Okay. And for in Ri possible, there are n minus I possible down steps, because you know that this is 0, 1, 2, 3, 4, something like that, because this is the farthest point that we can go, so we cannot really go beyond this line. So we have 1, 2, 3, 4, etc. possible down steps. That's what I meant over here. So it's like this is 0, 1, 2, dot, 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 like maybe I can 1, 2, dot, 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 n minus I. These are all possible down steps. Yeah, okay. So for instance, this, we have 1, 2, 3, 4 possible down steps for this. Here, 1, 2, 3, 4, etc. Okay, so 5, we have a bunch of observations, and okay, I think I should copy this, and then we'll look at this again. So, wait, did I make a mistake? Maybe something is off by 1. Is this, for instance, actually this is n, this is n, this must be n. This is, in this case, n equals 6, I think. N equals 6, k equals 2. Because the last index is n minus 1. So n equals, so let's see, n equals, I equals 2, 5. Then I think it should be plus 1, yeah, right? Plus 1. Because here, n equals, n minus 1 plus 1 equals 2. So we have 2 possible stuff over here. So I think it should be plus. Okay, so the thing is, the point here is that these are differ by 1. So suppose that we have only down steps, okay, in this region. Then we have 3 possibilities, but this is missing, right? And also here we have 4 possible down steps, but this is missing. So in every row, if you look at every Ri, exactly we have one missing down step like this, or we have this figure x, because figure x will contribute nothing to this. Where is it? Nothing to this, because 1 minus 1. So every if you look at every square here, we have at least one down step, or most of the time we have one down step only. But sometimes we have a missing square, missing down step, or we have to have the figure x, exactly 1. So that is the claim over here. Is that 6? Is that 5? 5. In Ri, there exists a unique, say, missing down step, or unique figure x like this, but not both. Because we have all the down steps, these two numbers must be the same. But otherwise, we have, because this is one smaller than this, either we have one missing down step or figure x that will contribute 0. So let's write down what those are. So here, this is the missing step. Maybe I can write it bigger. This is the missing down step. This is the missing down step. This is the missing down step. And this is the figure 8. This is the missing down step like that. So we always have a situation like this. And 6. Okay, now we will look at what happens if we have a missing down step. So, oh, by the way, this is K. This is K over here. In R1, we look at the first row here. This is not the ending point. This must be something. So either we don't have any down step here. So we have, there exists down step like this with ending point k comma 0, right? Like this. Missing. Let's write missing down step, just a red down step like this. Either we have this, maybe I can do, we have, let me just draw this using diagram. Or it's possible that there is a down step like this, right? But then you have to go this way, because this, you cannot stop here. That's not the ending point. So, or we have this. So the configuration at this point, k comma 0, we have either this or this. That's the only possibility. Okay, that's what I meant. And 7. If there's a missing down step like this, maybe I can draw it a little better. Then either we have one of these possibilities. So this this is missing, then okay. I think wait, I think my notes not very good. But let's say this is a comma I. We have a missing down step here. That means we have to have a minus 1, I plus 1. Sorry about that. A minus 1, I plus 1. Oh yeah, this one, yeah. In this case, okay, sorry about that. If we have a configuration like this, then we must have one of these situations. Here, this is a comma I. We have either missing down step like this, or Okay. Yeah. Yeah, it's not really good to draw all the diagrams. A figure X like this. So they are all here. These are the points. These are the how can I say, the reference points. Okay. If you have a missing down step, we have three possibilities. Why is that? This is missing, so that means okay, we have this may be missing. Okay, suppose that this is not missing, that there is something going on over here, right? And that means this path cannot go down, so it can go either this or this. If you go this way, so if this path goes this way, this cannot be there, because then it's an intersection. So we have this, or this doesn't go, then it has to go this way. But that means, wait a second, how is that? Oh, figure X. Oh, I think my statement is not correct. Instead of saying, yeah, the statement is not good. Sorry about that. If this is red, I think this is correct. Because missing by definition, that means it's not a figure X. Figure X means it's not missing, it's there, but it's with a crossing. So if this is a red thing, then we must have one of these situations. Either this is a figure X. If it's not a figure X, then we have to have this or this. That's what I said. Okay, let's continue and see what happens. 8. Okay, yeah, I think if this is missing, I think we can just forget about this. That's enough. Yeah, sorry about that. Yeah. Right. This is it. And 8 means that if you have a figure 8 configuration like this, then we have to have this must be missing, this must be missing, both missing, both this and this. And this is if this is not missing, then what happens? Oh yeah, because this means there are paths using this path, these steps. Figure X means that there are paths using that step. Okay, so by definition, this cannot be there, because then it will be a intersection point. So this must be missing, and similarly, this must be missing, because otherwise there's a path using this, there's a path using this. So it's, that's it. I think we are almost there. And 9. So yeah, here is the point. Now what I'm going to say is I'm going to put a dot over here, C. So C is k plus 1 over 2 minus 1 over 2, just like over here. And then D is the point over here. So D is 1 over 2, n plus 1 over 2. And then construct a path P prime from C to D by connecting the midpoints of missing steps. missing down steps. For example, maybe I can just draw this one more time so that you can see them separate. Actually, the idea is not difficult. So these are the missing steps. Okay. Let me put dots in the midpoints of the missing steps, but not this one. These are not missing steps. And then I'm gonna delete this, and then connect the dots like this. The step should be there. Like this. So we constructed from a non-intersecting lattice path, we constructed a path from C to D, okay? And the last observation is that the map sending the non-intersecting path to a path from C to D is a bijection from this to a path from set of path P prime C to D. Here using steps this is northeast, northwest, double north, just north, single north. Okay. You see, it can go either northwest, double north, northwest, north. Actually, the reason why this is a bijection, it follows from all the observation there. If you combine all the observations, then you can see that this must be a bijection. We get a path, and then once you have a path, you can reconstruct this, because north means that there is a figure X, and north step means there is a horizontal, and etc. Something like that. So it's a bijection. And an interesting thing here is that we have a nice weight structure. So lemma. Suppose P corresponds to this P prime. And then let's define the weight W of P prime to be the product of Bi for all this, and minus lambda I for all double horizontal. Oh, sorry. I think it goes like this. For instance, this the intersects with a line y equals I, okay, and this intersects two lines y equals I and I minus 1. And for this north step, double north step, we put the weight minus lambda I. For this north step, we multiply the weight Bi. So you take the product all of this. For instance, this doesn't have any weight. So in this case, what is the weight of this? This has weight minus lambda 2. This has weight B4. This has weight B5. Then what is the total weight of the sign, including the sign and the weight? This is the weight of P prime and delta n minus 1. Why is that? We have weight for every down step. Okay, so here, if we have all the ways, all the down step, all possible down steps, we would have weight lambda 1 to the n minus 1. But that's not the case because something is missing. Okay, so something is missing. So, but just pretend that we have like, okay. Just pretend, here we have n minus 2 down steps in the level 1, okay? And here we have n minus 1 down steps, and etc. So that gives us this. However, if we have a figure x, then we have one more extra down step because this makes, forces us to create one more down step. Okay, so that's why we have we multiply lambda 2, and this step means that there is a horizontal step like this that gives us weight bi. That's why this is the case. But the an interesting thing is, what is the sign? Sign is the sign of the permutation that we can get by connecting the dots. But figure x means if there is no figure x, that means the permutation is the identity permutation. But once you have a figure x, then you multiply transposition to the permutation. So whenever you have a figure x, you multiply minus 1 to the sign. And figure x corresponds to the double up step or double north step. So that's why we have multiplied minus 1 there. So all of these give us this lemma. Is that okay? So our next thing is to look at this path. But if you look at this may be familiar to you. This is something that we did before, only in a different form. So Favart tiling, it's just like Favart tiling with a slight variation of the weight. So another lemma. So we have this. For all path from C to D, if you add this weight generating function, then that's minus 1 to the n minus k, nu to n minus k. Okay, so proof. P prime is actually one-to-one correspondence with Favart tiling, n comma k. Because Favart tiling means we have domino or two types of monomial. So domino corresponds to this. This is a monomial. So you only look at how you only look at the height difference. So here we go one step. So it's a monomial, or it's red. This corresponds to red monomial. This corresponds to a domino. There's only one type of domino. And this red monomial, black monomial, like that. So it's exactly the Favart tiling. So what is the weight? The weight is almost the same, except we have different sign. If you remember, Favart tiling, they all have minus. For B's and lambdas, they all have minus. So this is okay, but we have to have the extra minuses there. But if you think about them, so just suppose P prime has R north steps, and S double north steps, like this. Then, by the way, K is the number of steps like this, because this is how you can go, you go from here to there. So that's K is that. So if you combine them all, R plus 2S plus K is the total height, which is N. So the sign of P prime is we only multiply minus 1 to S, because the minus only appears if you see double up step, double north step. But what is the sign of t? We multiply -1 to every step, every monomial like this or monomial like this. So it's minus r plus s. But if you think about them, what is the difference? Sign difference is -1 to r. S is common, so -1 to r. But what is r using this formula is -1 to n minus 2s minus k, but of course this is -1 to n minus k. So the weights are the same between this and this, only the sign differs by this. So that's why we multiply this. That's the proof. Yeah. Since generating function for t, weight t equals nu, we get the lemma. Now finally we are ready to prove the theorem. So proof of theorem. So what was the theorem? Theorem was originally this, but we restate it in this way. So we're gonna just, but we just computed this. So we will use the results there. Now we just combine all of these, proof just follows easily. Nu nk equals -1 to n minus k sum over p prime p prime. Yeah. Because we have to sum over this, but instead of this, we can just sum over this. So if you do that, then we only get this. And then here, this is going to be -1 to n minus k. Oh, okay. Yeah, let me write it this way. Yeah. This is going to be a sign. If you use that lemma, weight divided by delta n minus 1. But that's exactly the thing that we wanted. Because we know this part is the Henkel determinant, minor of the Henkel determinant. Comma, k missing, n, like that. So that's the proof, yeah. Yeah, there were some kind of technical details here, but the proof idea is essentially quite simple idea. Here, just correspondence between non-intersecting path and this. And all the details, technical details, are the things that this bijection works. Okay? So once you know the idea, you can just fill out all the details, and then you will do something that like I did. Okay? All right. Now let's see what we can say about this theorem. This theorem, I didn't tell you about the duality, but there is some kind of duality in this model. So let me tell you this lemma. This is a well-known lemma, sometimes called inverse minor formula. So let's say A is a square matrix, Aij, Ij from 0 to n, invertible matrix. And I and j are subsets of this set with same cardinality. Then the A inverse, there is the matrix A inverse, we can consider as minor I comma j. this can be computed in this way. I'm gonna explain what this means. And a j prime I prime over determinant of A, where I means sum of all elements in I, and a j I prime means the complement of the set I. This is a well-known theorem. And in fact, if the cardinality of I and both J, if their cardinality is 1, then this is nothing but the matrix inverse formula using cofactor inverse matrix formula. So if this is cofactor formula for A inverse, then you can always learn from a linear algebra course. Okay. So let's consider this situation. Mu I plus j, ij from 0 to n. Okay. Let's consider this situation. And then what is the determinant of A? That's the determinant of the Henkel determinant. So it's going to be the product of lambdas, but we can also write in this way, n minus 1, lambda 1, lambda n. We can write the determinant in this way. And then nu nk is minus 1 to n minus k, lambda 1, lambda n. That determinant of A, because originally it was the denominator was this, but I rewrote using this formula. Okay, and here it's a matrix A. This matrix is really the Henkel matrix, the finite Henkel matrix, and 0 up to n, where we subtract n. And 0 up to n, we remove a k. This is exactly the theorem that we proved, stated in a different way. But if you look at this part, and together with this is exactly in this form, with the ij of size 1. That means, let's pull out this common factor. And we can use this. That means A inverse. So here, this is J, this is J, this is I. So that this is J prime, this is I prime. So this is going to be Ij. But Ij both have size 1, so this is nothing but k comma n. Okay. So that means lambda 1, lambda n times nu nk is A inverse, kn, right? That means if you consider these are the entries of this, where n is the column index. So this means A1 an are the entries in the column of A inverse. So you can write down the last row of the matrix inverse of the Henkel matrix. So let's write that down. So this means that that's equivalent to saying that k from 0 to n, mu I plus k, nu n comma k equals delta n I lambda 1 dot 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 lambda. That's equivalent to this. That statement is equivalent. I rewrote the statement. But if you think about this, this is something that we can see from the orthogonality. This is equivalent to this statement. X to the I p n x equals delta n I lambda 1 dot 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 lambda n. Why is that? Because just imagine that you expand. This is nu nk x to the k. So these two combine together, x to the I plus k. But if you apply this, then you get this. But this is true. We know this is true because if I is less than n, this is 0. We know from orthogonality, and they are equal, then we get this. So this is something that we can see from this orthogonality as well. So our theorem is basically, what this theorem is saying is that a formula for the matrix inverse, say k comma n, where this is the A is the Henkel matrix, the finite Henkel matrix. So the natural question is, can we find any entry like ij? So that's the question. What about any rs? Well, we can do the same thing to get a formula for this. Let me explain that a little bit. Okay. Theorem. Actually, there's a theorem. I can just take the theorem right away. Let A be the matrix mu I plus j, ij from 0 to n. Then the A inverse has the entry r comma s, sum over k from 0 to n, nu k comma r, nu k comma s over lambda 1 dot 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 lambda k, like that. So if s equals n, what happens? Is s equals n, then this must be greater than or equal to n, this element, otherwise it will be 0. So the sum, we have only one non-zero term. K must be n. This is n, and this is n, so this disappears. K, n, and this is up to n. That's exactly the formula that we obtained before. So it's a generalization of that. And yeah, I'm gonna just give you a proof of this. Proof. But only the sketch. I'm gonna sketch the proof. Again, you see the matrix is like you delete row or column, or the rth element, rth column, or s row, things like that. So we need to do some setup. So let's say I is r, the one element, j is just the one element, s, and what is the matrix? What is the matrix entry of this inverse? Then using the inverse minor theorem, r plus s, a j prime I prime over determinant. So we need to look at this. But this is the Henkel determinant, Henkel matrix, so we basically subtract one entry, one element there, one element from the row, column, like that. So let s to be a n minus 1, b r, b n minus 1, where ai is, originally it was I comma 0, but we have to do some shifting. If I is greater than or equal to s, we subtract one more. This I plus I greater than or equal to R. We shift the points by 1 if they are greater than S or R. So, by the LGB lemma, the matrix entry or minor is the generating function for all non-intersecting lattice path from AS to BR, the sign and weight. But then we can also consider this diagram. Let's see. Yeah, it's not so easy to draw, but let me draw anyway. This is missing one. This is 0. This is S, minus S. This is minus N. I think I need some more space. 1, 2. This is R missing. 2, 3, 4, 5. This is N. So we go all the way up. And all the way down, like this. Yes, maybe I missed one point. Oh, yes, sorry about that. Yeah, this must be this. Yeah, I think this is N, minus N. And this must be like this. And up. This is going to be K. This is our K. Yeah, something is slightly off. Maybe I should have copied this and yeah, I think it was a bad idea to create this just right now. I think I can just show you. This one, okay. Where is it? This one. There it is. Can I take a screenshot? Yeah, let's start over. Okay, great. So that's it. So we have an example like this. So the point here is that now these points, there is a missing point here. And also there's a missing point here. So before they all go up, except they are all fixed, but they can now go somewhere. But the thing is, in this, if you look at the horizontal, the vertical line, not every point is occupied. For instance, this is missing. So that means this is missing and this is missing, but if you look at this part, that's exactly like this. But except this becomes K, this becomes R. So this part becomes new K comma R. And also if you look at this, that's exactly the mirror image of this. So it goes from K to S. That's why we have things like this. So let me just let's ignore this. Let me write it down. So, okay. Yeah. So this part, is equal to sum over all K. Actually, this must be from max Rs to N. And I'm skipping some details. So one part contributes to new KR, and the other part contributes to new KS. Okay, but if you but this is actually exact formula that we want over here. So they cancel each other like I think I made a mistake over here. This will cancel with the signs over here, so everything works out. So that's the proof. And there are some details, technical details you need to check, but the idea is just that simple. And also, this can also be proved using orthogonality. So what does this mean? This means if you multiply the two matrices, then you get delta and delta RS, things like that. That can also be proved using just the orthogonality. Yeah, that's maybe we have some time left, so I can go over the proof here using orthogonality. There's also some interesting computation in this proof, so I'm gonna tell you. So we need to show that this, if you multiply two matrices, you get delta R comma S for the entry RS. So this is K from 0 to N, mu R plus K, A inverse R, KS. So this is our matrix A, R comma K. This is our matrix A inverse KS. So this is something that we need to prove. But this, if you plug in the formula here, then you get this. New LK, new LS, lambda 1, lambda L. I just plug in the formula there. So, but this, because of this, we can think of this as x to the R plus K, but using the linear function. So that's the right-hand side is L of summation K from 0 to N, x to the R plus K, sum L from 0 to L, N new LK, new LS over lambda 1, lambda L. Now we can separate this in this way. X to the R, I'm going to separate that over here. And I'm going to write L first. New LS, lambda 1, lambda S, and then K sum. X to the K. I just separate these two like this. But if you look at this, this is nothing but PK. Okay? So this is, and also I'm gonna rewrite this, because x to the k can be written as a, sorry, x to the r can be written as a sum over PA. But here, this is the moment, mixed moment RA. Okay, so here we can write it down. A from 0 to R, mu RA, PA, and sum L from 0 to N, lambda L, sorry, this is L. And finally, this is PK. Oh, sorry, this is L, sorry. Now, we have just constant, these are all constants. We have two orthogonal polynomials multiplied. So because of the orthogonality, A and L must be the same. So we only need to look at L. So sum over L. And also, because of that, we can forget about the linear functional. So L from 0 to N. A is L now, R comma L. And new L comma S. And if you have L, their linear functional gives this exact this quantity. So this is it. This is all. But we know that they are orthogonal. They are orthogonal each other. So this is RS. That's the proof. So using the computation, we can also confirm the formula this way. Okay. Yeah, so this is some kind of duality between Matskin path, or sorry, moments and coefficients. So, yeah, I think that's enough today. Thank you for your attention.